and he's going to tell us about a new approach, small black holes in string theory.
Thank you. Hello, Ron. First, I would like to thank the organizer for having me here. Today, I'm going to talk about my recent work with my advisor, David Kudasov, on these two papers. So here are the contents. To begin with, let's first recall that to study gravity theory in flat space-time, it is often useful to consider Euclidean signature within a symptotic RD process 1. And here, this tau denotes the Euclidean time. And this Euclidean time has a circumference of denoted by beta fixed at infinity. And under these boundary conditions at infinity, we can solve the classical solutions, which are crucial for understanding the canonic ensemble of the gravity theory. And this beta is identified with the inverse temperature of this canonic ensemble. One famous example of such classical solutions is the Schwarzschild solution. Specifically, it's a solution of general relativity and is given by this metric. So here, this Euclidean time tau is identified with tau plus beta. When the radial coordinate r is at infinity, you can see that g tau tau is equal to 1, which means that the circumference of tau circle is fixed to be beta at infinity. As r goes inward, g tau tau decreases, which means that the tau circle starts to shrink. It shrinks to 0 size at some finite radius, denoted by RH, also known as the horizon radius. So now we have two parameters, RH and beta, but they are not independent of each other. So actually, for the geometry to be smooth at the horizon radius, they have to satisfy this relation between RH and beta. Furthermore, I would also mention that for quantum gravity effect to be suppressed, we need to require that beta is much larger than the Planck length, LP. In weakly coupled string theories, there's another scale, namely the string length denoted by LS, and it is much larger than the Planck length LP. So as a result, for example, the previous Schwarzschild solution receives string corrections, for example, as calculated by Calvin Myers Perry. These corrections are negligible only when beta is much larger than LS. And when beta approaches LS, string corrections become significant. So one natural question is how these corrections alter the black hole solutions, and that would be the question. That's a question I'll be focusing on in my talk. And as we'll see, this winding number 1 string will play a very important role in answering this question. So let me first review some previous efforts in answering this question. Let's first consider a string with winding number 1 in this flat space-time RD cross S1. So again, we have the Euclidean time, which is identified with, which has the periodicity of beta. And here I only draw two coordinates, the radial coordinate and the tau coordinate. And we are considering a string which is wound around this tau circle. So this kind of string. And I will denote it by chi. So the mass of this chi is given by this formula. And in this formula, the first term is just the tension square times the length of the string square. So this corresponds to the energy of just some anti-classical string, basically. But so we know that the fundamental string in string theory is not just a classical string. So so the second term actually captures the quantum effects on the worldsheet. And in the second term, this constant beta h is of order LS. For example, in bosonic string theory, it is equal to 4 pi LS, and in type 2 string theory, it's equal to 2 square root 2 pi LS. So if we just have some trivial background RD cross S1.
Sorry, can I ask a question?
Yeah.
Is there an intuitive argument for why quantum fluctuations should decrease the mass? Maybe it's obvious.
I think so. So first, in bosonic string theory, it's just like some generalization of the harmonic oscillator. And in that case, we know that the 0 point energy is negative.
Okay.
Yeah, and I think similarly is true in type 2 string theory, but the subtlety is that usually we say GSO projection would project out the tachyon state, but if we consider winding string, the GSO projection is kind of opposite of the usual as the GSO projection. So it cannot project out the tachyon state.
Okay, thanks.
Yeah, so if we have a trivial background RD cross S1, the winding number would just be conserved. But if there's a black hole, a winding string can be unwound at the horizon radius. That place the Tor circle shrinks to zero size. Recall the previous cigar geometry, where the Tor circle shrinks to zero size at some radius. So what this means is that the black hole solution breaks the winding symmetry spontaneously. And as a result, the winding string chi gains a non-zero expectation value near the horizon radius. At low temperatures, this winding string is very heavy. So its mass is basically just this length times the tension 1 over 2 pi alpha prime, so which is very large. So its expectation value decays rapidly at large r. More specifically, it decays exponentially with this characteristic length given by alpha prime over beta, which is very short. And from this exponential behavior, we can say that this winding string chi is just is some non-perturbative alpha prime correction to the black hole solution instead of perturbative correction. So as the temperature goes up or the beta decreases, the mass of chi also decreases. So in this case, the expectation value of chi is turned on in a wider and wider range. For generic beta of order LS, all string corrections are fully turned on, either perturbative or non-perturbative corrections. In this situation, the problem would be very complicated. However, if beta is close enough to that critical value beta h, the two terms in the mass formula kind of balance each other and make the mass of chi arbitrarily small. So in this case, the effect of chi suppresses the perturbative alpha prime corrections and make the problem simpler. And indeed, it is easier to study the black hole problem near the so-called Hagedorn temperature, which is just the inverse of the previous beta h. Or in other words, beta h is just the inverse Hagedorn temperature. And that's the reason why the beta h has this subscript h. This h just denotes Hagedorn. So let me first briefly review the Hagedorn temperature. So in string theory, we know that for a heavy string, its entropy follows the Hagedorn behavior, which is proportional to its mass, where the proportionality coefficient is exactly the previous beta h. Then if we consider the partition function, which is given by this integration of the mass, we can see that at high energy, the integrand behaves exponentially. In particular, for if beta is smaller or equal to beta h, that integration would diverge. So this means that this beta h is somehow the limiting temperature in string theory. So that's the significance of such a value. Come back to the black hole problem. So near that Hagedorn temperature, one can write down an effective field theory to study the problem. So first, as I mentioned, near this beta h, the winding string is very light, so it should be considered. It should be included in this EFT. Second, it's useful to parameterize the inverse temperature using this phi. So this phi is basically the deviation of the inverse temperature away from beta h. So in terms of this phi, we can rewrite the mass of chi from the previous formula to this formula, where you can see that to leading order in phi, the mass square is just linear in phi. And for example, it's just a simplest example. If phi is equal to 0, which means that it's at Hagedorn temperature, the mass of chi would just vanish. So, but the point is that this phi is actually it can actually vary locally in RD. So it's actually another dynamical field. So it's basically just G Tor, because the beta is the circumference of Tor circle, and it can vary locally. So now we have two dynamical fields, chi and phi. For the interaction between them, we can look at the mass term of chi, which as I said, to leading order is the mass square is proportional to phi. So this gives rise to a cubic coupling between phi and chi. Furthermore, reducing on the tall circle, because the tall circle is very small, to reduce on it, we can write down an effective Lagrangian. And to leading order in the fields chi and phi, this effective Lagrangian was written down by Horowitz-Polchinski and take this form. So the first two terms are just the kinetic terms for phi and chi, and the last term is the previous cubic term. So this is usually called Horowitz-Polchinski action in literature. And now we have the theory. So the next step is, of course, to solve the classical solution in order to compare with the Schwarzschild solution, which is classical solution for black hole. So next step is to first write down the equation of motion and solve it. So it's actually very hard to get some analytic solution. So what people usually do is just to solve the equation of motion numerically. And the solution that we want should be normalizable. That's apparent. But furthermore, for simplicity, we want to find a solution that preserves the spherical symmetry, just as the Schwarzschild solution does. Which means that the fields chi and phi only depend on the radial coordinate r. And these solutions are usually called the Horowitz-Polchinski solution. And the importance of them is that they are expected to answer how the Schwarzschild solution look near the Hagedorn temperature. And maybe one difference between these two solutions, between the Horowitz-Polchinski solutions and the usual black hole solution, is that the Horowitz-Polchinski does not contain any horizon, which means that the fields persist to the origin. Then the regularity at origin requires that the fields have zero derivatives. So that's some boundary conditions, basically. Then it turns out that for any value of chi at origin, only discrete values of phi, 0, can yield normalizable solutions. And for other values, the solution would just blow up. And we, as people usually do, just focus on the simplest case where this field chi has a monotonic profile in R. And there also exist profiles where chi is not monotonic. And that is actually an ongoing work with Badria, Kudasov, and Wu. But that's not the point of today's talk. So let's just focus on the simplest case of solution. Let me show you an example of solution. We just take some specific spatial dimensions, d to be 3, just as our universe does. By the way, here d basically denotes the non-compact dimensions. So I'm assuming that there are also some internal extra dimensions which are compact. That's not included in this d. So in 3 dimensions case, we first take chi 0 to be this small value, namely 0.01, and then tune phi 0 in order to get a normalizable solution. And from this plot, you can see that the asymptotic value of phi, which we denote phi infinity. By the way, this phi infinity is basically the deviation of the temperature away from Hagedorn temperature. It will be a very important parameter for the solution. So this solution has phi infinity positive. It means that the solution is at a beta larger than beta h. And furthermore, for the other solutions with different values of chi 0, they all lie at beta larger than beta h. Why can they not lie at beta, for example, beta equal to beta h? So the fact is that when as beta approaches beta h, the fields will just vanish everywhere, so the solutions just become trivial. And that's the reason why there's no solution at the Hagedorn temperature. So this is the behavioral solutions at d equal to 3. And actually for d equal to 4 and 5, the Horowitz-Polchinski solutions behave similarly.
Sorry, so for small r, where phi is negative, That means that the temperature is above the Hagedorn temperature?
Yeah, locally is above Hagedorn temperature. Yeah, what about larger d? So first, at d equal to 6, we found that for all solutions, the phi infinity is exactly equal to 0, which means that all solutions only exist at the Hagedorn temperature. And by the way, they take such an analytic form. But this brings an issue. So the issue is that we know that black hole solutions certainly exist for t equal to 6 and arbitrarily low temperature. So the fact that Horowitz-Polchinski solutions can only exist at this particular temperature seems to say that it is not related to the black hole. And even worse, for larger d, there are no normalizable solutions at all. So this solution at d equal to 6 at least is normalizable, but for d larger than 6, there are no even normalizable solutions. On the other hand, we actually know how the black holes look at large dimension, even at string scale temperatures. To see that, we can take the Schwarzschild metric and also take the large d limit. And in this limit, we can find that there's a near horizon region whose volume is basically given by d. So if d is infinite, there's a large near horizon region. And the point is that this large region can be described by the so-called SL2 module 1 WZW model on the worldsheet. And the level of this WZW model K is related to the inverse temperature beta. So it was found by Young, Miller, and Tanabe. The point is that this WZW model description remains valid all the way to string scale temperatures, which just corresponds to the level K of some order 1 value. And this is described in the paper by Chen and Medicina. So we see that certainly there exists black hole solution even near Hagedorn temperature at large d. But on the other hand, we found that Horowitz-Polchinski solutions do not exist at large d. What's the problem? So actually, this problem has already been solved by Bathilda, who actually was a postdoc here, and Kudasov and me. So in particular, we found that the quality corrections to the previous Horowitz-Polchinski, the previous Horowitz-Polchinski action actually is just to leading order. But we found that the subleading terms, which are some quadratic terms, they can resolve the issue. So first, let me show you explicitly what the quadratic terms look like. This was calculated by Bruce and Zygdom. And by the way, there's also some even older paper by Klebanov and his collaborators trying to calculate similar things. So from the calculation, there are two new terms. One is phi square chi square, and the other is chi to the 4. They are both quadratic terms. And the effect of them is that they bring some non-zero corrections to the previously vanishing phi infinity. So that's a good news, because now we know that at least when d is equal to 6, the Horowitz-Polchinski solutions remain below the Hagedorn temperature, because phi infinity is no longer 0. It's actually positive for all solutions.
Sorry, why can you neglect higher order terms in the potential, since here you are balancing cubic and quartic, right, to find the solution?
Yeah, that's an interesting question. We'll see why in the next page, hopefully. Yeah. So what about larger d? So to further investigate the situation, we continue d to non-integer values, namely 6 plus epsilon. And when epsilon is much smaller than 1, we found that the solutions exist both below and at the Hagedorn temperature. And in particular, at the Hagedorn temperature, the field values, for example, at origin, this chi 0, phi 0, they scale as epsilon. So it means that as long as epsilon is small enough, specifically for epsilon equal to 0, the fields are still very small, and that's why the higher order corrections, such as chi to the 6, are negligible, and it's okay for us to just study the quadratic corrected effective action. And by the way, regarding the balance of quadratic and cubic term, this story is somehow similar to the Ginsburg-Landau theory. So somehow there's there's some coefficient of the cubic term kind of vanish at this critical dimension d. And that's why quadratic term becomes important, but higher order terms are still negligible. There's some sort of story like this. But for any integer d larger than 6, this epsilon would be of order 1, then this scaling behavior would imply that chi 0 and phi 0 are also of order 1. So in this case, of course, the higher order terms are no longer negligible, and we have to include all of them to further investigate the situation. And that brings us to our recent work, where we have made progress towards deriving the full effective action. Is there any questions so far? Okay, so let me proceed. So it turns out that the higher order terms, which by the way also includes terms with more derivatives, are very hard to compute. But to make progress, we actually utilize the symmetry of the worldsheet CFT. To see such a symmetry, let's first use a capital X to denote the scalar field on the worldsheet corresponding to the Euclidean time tau. Then we can write down the vertex operators corresponding to the previous two fields, chi and phi. For the field chi, it is just given by some tachyon vertex operator, where the left moving part and right moving part has opposite momentum charge, so that together they can give a winding number 1. For the field phi, previously we have seen that it controls the local circumference of tau circle, so it's basically just g tau tau. So the vertex operator is just given by the graviton. So this phi, which is g tau tau, is just a graviton, total part of the graviton. So it's given by the graviton vertex operator, which is partial x and partial bar x. So the point is that these j plus, j minus, or g3, or maybe denoted by ja together, these kind of operators satisfy the SU2 cosmology algebra for both left moving and right moving parts. So specifically, their OPEs take this form. And here, the level of this cosmology algebra K is equal to 1 for this particular case. So this symmetry allows us to use the word identity to calculate any correlation functions involving these vertex operators JAs. So specifically, we have this word identity, which is basically a recursion relation. So on the left-hand side is an n plus 1 point function, and on the right-hand side, the first term is n minus 1 point function. The second term is n point function. So this is a recurrent relation reducing high point function to low point functions, and allows us to calculate any n-point function. So, and what we are able to do is to derive the effective Lagrangian, but only to leading order in 1 over k. Of course, that's not enough since I've told you that k is equal to 1. And by the way, for bordonic string, k is equal to 1. For silver string is actually a little bit better, is equal to 2 also. But anyway, these values of k are some order 1 values. So in this case, of course, higher order terms in 1 over k are not negligible. But the strategy we consider is just to take the large k limit. This is in the same spirit of the often used large n approximations in QFT. So we just take the large k limit. I hope that we can still get some result that is qualitatively true in the original k equal to 1 problem. So let's do it. First, we can calculate the kinetic term in the Lagrangian. So the kinetic term takes this form. So in this form, the coefficients g chi chi star and g phi phi are given by the 2-point function of the corresponding vertex operators. For example, this g chi chi. Oh, by the way, maybe I should mention, so chi is a complex field actually. So the winding string can have winding number 1 or minus 1. So the string with winding number minus 1 is this chi star, this complex conjugate. So this g chi chi star is given by the 2-point function of the vertex operator for chi and the vertex operator for chi star, for example. And this two-point function is not in the original SU2 theory, and actually it's in the theory deformed by chi and phi. So the deformation to the worldsheet Lagrangian is this form. For example, we have this term the perturbation of chi is given by this chi times its vertex orbit. So chi is basically coupling on the worldsheet. By the way, here I've neglected some factors like minus sign or square root 2. And you can see our papers for details. Furthermore, for people who are familiar with this kind of model, let me mention that this actually is something called non-abelian Thirring model, which is widely used in CFT. So to calculate that two-point function, we can expand it as power series in chi and phi. So each term in the power series is just an n plus 2-point function in the undeformed theory. So here n denotes the power of chi plus the power of phi. So each n plus 2-point function, to calculate them, we can just apply the previous wide identity. That gives us the recursion relation, right? And we can resum the both sides of the recursion relation. That will give us the full expression of the original two-point function. So this is the final result. Very simple. And by the way, you can see that there are some singularities at finite values of chi and phi. For example, when chi is equal to square root 2 over pi, this g chi chi star will just diverge to infinite.
But isn't that the metric? I mean, the first one, the metric of the hyperbolic plane, the hyperbolic plane, half plane, or disk.
You mean this?
G chi chi, yeah.
Actually, I didn't check.
That's just the disk, right?
Oh yeah. That is true.
So yeah, it doesn't have singularities in reality. I mean, it's a metrically complete space.
Yeah. Yeah, that's true. Yeah, the singularity is just in the sense that this value is diverges.
But the metric is not the curvature.
Yeah, the curvature is constant everywhere.
Yeah, and by the way, for this phi we can redefine phi so that g bar phi is equal to 1. In the meantime, the new phi has a range from negative infinity to positive.
So maybe by singularity you mean like the asymptotic region of
Yes, it's asymptotic.
Yeah, actually that's what it's not some finite singularity, I guess. So this is kinetic term, and this second we can also calculate the potential term in the Lagrangian. That is given by this vacuum amplitude on the worksheet. So we just consider the tree level amplitude. So this vacuum amplitude is again in the deformed theory of the worksheet, but we can write it in this form where we just insert this exponential of the worksheet Lagrangian deformation in the undeformed theory. So again, this form makes it clear that we can Taylor expand it and write it as a power series where each term is an n-point function in the original theory. So again, for each n-point function, we can apply the Watt identity and then perform a resummations of the both sides of the Watt identity to give the full expression of the original power series. So this is final result for this potential. And again, you can see that when phi is equal to that critical value, or chi is equal to that critical value, square root 2 over pi, this potential also diverges to infinity. But another fact I want to point out is that this factor, 1 over k alpha prime, means that the length scale is square root k LS. So at large k, length scale is pretty large. So high derivative terms are negligible. And that's why I didn't even bother talking about them. So just two derivative terms is enough. So let's collect the kinetic term and the potential term. And also don't forget about the other massless fields, namely the dilettante and the graviton. So they together give the four Lagrangian. So the first two terms in the Lagrangian is basically just the dilettante gravity. The last two terms are the previous kinetic term and potential term. So this is basically a theory of kind phi coupled to dilettante gravity. So with this Lagrangian, we now have the power to do a lot of exercise. The most important thing is just to solve the classical solutions and to explore the region that we are not able to explore previously. Okay, so basically the last part I'm going to show you is the classical solutions. Well, again, we still solve it numerically, but the important thing is that there are many crucial properties of the solutions. And there are some implications in the black hole fundamental string transition. So, by the way, is there any questions so far? Okay, so to solve the theory, we can first do some simplification. First, just as before, we consider the spherically symmetric case. And in that case, the metric can take this form. So we are basically defining the radius of the d-1 sphere as this r. Then we can no longer fix GRR to be 1, so let's just let it be a field denoted by h. So now we have four fields, h, chi, phi, this h, and the dilettante capital phi. So we have four equation solution to solve. It sounds like there are too many equations, but the situation can be simplified. So first, the equation solution for h is actually algebraic, which means that it does not involve any derivative of h. So this allows us to just express h in terms of the other fields. And we are done. So now we have three second-order differential equations to solve the three equation solution for chi, phi, and capital phi. So it required 6 boundary conditions, for example, at r equal to 0.
Just to be clear, so in this theory, the thermal circle does not exist, it's phi, right?
Yeah, that's true. But in this case, we have this SU2. So we kind of has some three sphere instead of just S1. So of course, we lost the meaning of inverse temperature, something like that. But we think that so in this theory, the important parameter is phi infinity. And we think that is some analog of the previous inverse temperature. So recall that in the original problem, phi captures the deviation of inverse temperature away from Hagedorn temperature. So we think in this theory, we still have phi infinity, and it can play the similar role as the previous deviation from Hagedorn temperature. Yeah. So here we have 6 boundary conditions to solve. It still sounds like there are too many boundary conditions, but actually a lot of them can be fixed. First, we can utilize the shift symmetry of dilettante capital phi to fix capital phi at origin to be any value that we like. And we like 0. That fixes one boundary condition. And furthermore, just as the situation in the original problem, this regularity at origin fixed the derivatives of the field to be 0. So this further fix 3 more boundary conditions. So we are now left with just 2 boundary conditions to impose, and we choose them to be chi 0 and phi 0. Recall that to solve the original Horowitz-Polchinski problem, we also need to kind of tune chi 0, phi 0 to find the solution. So the current theory is not more complicated than the original leading order theory. I mean, technically it's still very feasible to solve them. And to solve them, we need to choose. So for generic chi 0, phi 0, the solution still blow up at large R. And we need to find the correct values of chi 0 and phi 0 to get normalizable solutions. So technically, this is basically a fine-tuning problem. So let me just show you the example of the solution. First, I'm going to start with the subset of the solutions which has phi infinity equal to 0. this is an analog of the solutions in the original problem at Hagedorn temperature. Just as I said, phi infinity is some analog of the deviation away from Hagedorn temperature in the original problem. We focus on this subset, and here's the solution has some d. So for example, I take d to be 6.5, and we have this solution. This kind of phi are related linearly, actually, and they decay to 0 at large R. This dilaton capital phi starts from origin, starts from 0 and decreases, and converges to some negative constant at large R. So this is a solution at d equal to 6.5, but we want to know the solution at all d. So in order to do that, I plot the field values at origin, namely this chi0 and the dilaton at origin, as a function of dimensions. So first you can see that as the dimension goes to 6, the fields vanish. So this capital phi, of course, vanish, and this, note that this vertical axis is not chi0, it's 1 minus some factor times chi0. So this combination goes to 1, meaning that chi0 goes to 0. So that's why I said as d goes to 6, the fields all vanish. And this is similar to the situation in the original Horowitz-Polchinski problem. Recall that I've told you if we take d to be 6 plus epsilon, the chi0, phi0 will scale as epsilon. So as epsilon goes to 0, the chi0, phi0 go to 0. So there's a similar situation, but what's more interesting is that we found another critical dimension, which is at 7. And by the way, there's some numerical uncertainty, which is not very large, pretty small. So at this critical dimension, as d approaches 7, we can see that chi0 go to the critical value where the both kinetic term and potential term diverge. So this chi0 goes to square root 2 over pi. That's precisely the previous critical values, or in your language, the boundary of the hyperbolic is something like that. And in the meantime, the dilaton diverges to infinity. So what does it mean? It means that the Horowitz-Polchinski, this kind of Horowitz-Polchinski type solution cease to exist at this critical dimension d equal to 7. Furthermore, we can release the condition phi infinity equal to 0 and see how the solution change with phi infinity. So let's take d equal to 6.5 as an example. And in this example, we find another interesting fact, which is that there exists a maximum value of phi infinity, which is approximately 0.0033. And as phi infinity approaches this maximum value, the solutions again become singular. For example, chi0 again approaches the square root 2 over pi, and the dilaton diverges to infinity. So it means that at each value of d, Horowitz-Polchinski type solutions only exist a finite range for phi infinity from 0 to some finite maximal value. And what we do furthermore is to get the maximal value of phi infinity as a function of d. That corresponds to this dashed line. So at each value of d, you can see that the solution can only exist from here to here, for example. And together, this region below this dashed line highlights the existence of the Horowitz-Polchinski type solutions. So the Horowitz-Polchinski type solution can only exist below this dashed line. Actually, so in my original slides, this should be a shaded region, but somehow it cannot be displayed on the screen. But it's okay, it's not a problem. It's just that there's a shaded region below this dashed line. Okay, so
the shaded region is smaller than the colored region?
So this is some green color, right?
Oh, okay.
So this green
so
color
the
is
same information. Okay.
Yeah. Yeah. So this is I guess the main result of our recent work, and what's the lesson of it? So I think the lesson that we can learn from it is that in the original Horowitz-Polchinski problem, we should expect the similar behavior, namely the Horowitz-Polchinski solution can also not exist for arbitrarily large d or arbitrarily low temperature. Recall that phi infinity is like beta. So large phi infinity means large beta or low temperature. But it seems that, but by the way, let me point out that this is unlike black hole solutions, which of course exist at any d and arbitrarily low temperature. So it sounds like the Horowitz-Polchinski solution is not related to black hole. So why did I waste 1 hour talking about this Horowitz-Polchinski problem?
So just a quick question. So this result does not depend on k?
Wait, so this is only a concrete result at large k.
Okay.
But we still expect that for finite k, there exists some, for example, critical dimension. Maybe not 7, but some other value. So qualitatively, we still expect an existence of such a dashed line. To
Is there an expectation of what critical dimension would be for the k equal to 2 case, the supersymmetric case?
Sorry, can you say again?
Is there an expectation for the critical d, like in the type 2 case, k equal to 2?
Actually, yeah, I think actually we expect. Yeah, I'm not sure. We don't have any expectation, but maybe one expect. So actually, I talked to Wolfer about this. His expectation, I can tell, is that d at k equal to 1 or 2 is critical. Sorry,
Will you say it's 5?
you mean the critical dimension?
Yeah.
He will say that it should be larger than 10, because yeah, actually I don't, because from some Swampland point of view, if we start from the black hole and decrease beta, it should somehow has to encounter some phase transition into another classical solution, which is a Horowitz-Polchinski solution. So in order for this kind of phase transition to exist, we have to have the existing Horowitz-Polchinski solution at equal to 10. I think that's basically his point, but I think there's still, there's definitely something to understand regarding this point. Maybe we can calculate the 1 of k correction and see if this critical dimension decrease or increase.
K is also controlling the suppression of the higher derivative terms in the effective action as well.
Yeah.
So presumably, since K here is low, it's 1, then there should actually be higher derivative corrections to this score.
Yeah. So if k is not large, we should have corrections to the potential. We also have correction to the 2 derivative terms to connect them, and we should also have higher derivative terms, which cannot be neglected. Yeah, there are many complications for finite k. So now we are at the point that we are at a very, I guess, negative point. So this somehow means that the Horowitz-Polchinski seems not related to the black hole, but we actually don't think so. So I think it actually presents a natural picture where the black hole lives on the other side of this dashed line, and when it crosses the dashed line, it can encounter some phase transition into the Horowitz-Polchinski solutions. But in other words, the black hole solutions, the Horowitz-Polchinski solution, kind of complement each other in different regions. So,
has this something to do with the expected, sometimes this black hole string transition?
you mean the Swampland thing?
Yeah.
Yeah, I think they would say that's, actually that's something which I don't quite understand. Somehow there exists some species scale, which means that, so in weakly coupled string theory, there's a species scale which is just the string length, and if the temperature approaches the string scale, there has to be some string tower or something to get the black hole transition to some other classical solution. Actually, I don't quite understand that point, but that's basically the logic, I guess. It involves some, conjecture regarding the relation between species scale and some towers, some tower.
Right, so suppose that the original, I mean, the old argument that is decades old, was that at some, when the black hole becomes smaller, right, its entropy is less than the entropy of a long string. You expect transition to the most probable state. And also the size of this long string, right, it grows with the energy up to logarithms. So at some point will become bigger than the black hole. But I imagine that this was, I mean, Horowitz-Polchinski was an attempt to make this more precise.
I'm not quite sure, because in that case we need to look at some microcanonic ensemble, namely we vary the mass and look at its entropy. But here we basically look at the canonic ensemble. We fix the temperature and look at the free energy. So I'm not sure if that situation can be translated to this canonic ensemble. Because in canonic ensemble, the free string can lie at the Hagedorn temperature, exactly at the Hagedorn temperature, I guess. So I'm not sure how to argue a similar thing here.
Would you also have something to say about what happens in type 2 strings and whether there is a phase transition, a string black hole phase transition?
You mean here I only talk about bosonic string? Yeah, that's true, but we expect that in superstring case we should have similar result. Maybe the critical dimension is no longer 7, but there should also exist a critical dimension.
Because a few years ago there was an argument with...
Oh, you mean Witten's
yeah.
I think their story is kind of consistent with what we got. So I think they seem to say that in type 2 string theory, right, if we start from a black hole and decrease beta, the dilettante classically it cannot become Horowitz-Polchinski solution smoothly. So maybe one possibility is that the classical solution is not valid. In other words, the dilettante diverges at some point and quantum effects become important. And that's exactly what we found. So as we approach the dashed line, the dilettante diverges to infinity. So I think that's consistent with Witten's Witten's story. Of course, they also say that in hydraulic string, it's still possible for black hole to transition into Horowitz-Polchinski smoothly. Yeah, I don't have anything to say regarding that case, but that is not inconsistent with what we got, at least. Yeah, so we have this natural picture, and one evidence pointing this picture is that in our large K problem, there actually exist solutions which are analog of the black hole solutions. To see that, we can reparameterize the metric in this form. So this is basically saying that we now fix G rho or GRR to be 1, and let G omega omega be some field denoted by psi. And this rho naught is some arbitrary length scale. So with this form, we can rewrite the dilettante gravity part of the Lagrangian. It is very complicated, so just forget about this. But the point is that in the regime where psi is much smaller than d, which we have forgot to mention. So only say that there exists solution which are analog of black holes at large d. So if we already take d to be large, there exists a very wide regime where psi is much smaller than d. And in this regime, we can simplify this dilettante gravity part, which is take this form. And what is this form? So this form is basically just the Lagrangian for dilettante with some cosmological constant denoted by lambda, right? And we actually know that Lagrangian gives rise to some linear dilettante background. And this linear dilettante background, together with the other parts, namely the SU2, they can together give rise to something called CHS geometry, which is found by Cullen, Harvey, and Strominger. This geometry can describe a near horizon region of K and its fibrant. So this is indeed and some analog of the black hole solutions, and that exists at large D. So it means that in our large K problem, we have this kind of black hole solution on the other side of the dashed line that kind of support our natural picture. So this is basically the thing I want to share with you today. So I guess finally I want to mention some work in progress. We don't have a complete story, but I hope that maybe some audience here can make some comments or useful ideas for this kind of thing. So currently we are thinking about two problems. Okay. So the first problem is regarding the consistency of the full string theory in our large K problem. So in our problem we have this SU2K WZW model, right? And we take large K. So the central charge is slightly smaller than 3. So you know that in the full string theory the central charge should be 25 or 10, but anyway it should be some integer. So in order to compensate such a small deficit, we should have some other speculative CFT that has a central charge slightly larger than the integer. In the meantime, for this CFT to be a good speculator, we should not easily excite some massive states, right? Which means that there should still be a finite gap in this CFT. So the question that we want to ask you is that, does this kind of CFT exist? And we don't know any example of this. If it does, maybe another question to ask is that, can we prove a theorem so that if we have CFT whose central charge is close to an integer, then its gap is also small? Can we prove such a theorem?
By gap, you mean not the gap above the vacuum, but the gap, above the first normalizable state, right?
Yeah.
Otherwise, you can take the SL2 CCAR CFT, SL2 mod U1s. Those ones are 3 plus 6K, 6 over K.
Yeah.
They of course have long string modes.
Yeah.
You mean theories that don't have an SL2C vacuum?
Yeah, don't have a normalizable SL2.
Yes.
We do want normalizable SL2 C vacuum. Actually, a similar question is that if we start from some ADS with a very large, very small curvature, so that the central charge also is slightly above slightly above some integer, then can we have some speculative CFT whose central charge is slightly smaller than integer while still have a finite gap? So that's somehow related to distance conjecture or some distance conjecture or some work by Barfa. We're not sure. We're also not sure about the answer to that question. But if one can answer that question, that would also be interesting. Maybe. So this is the first question, and so again, the second is not actually a question. It's some work we're working on related to cosmology. And by the way, I took a screenshot of your website of this cosmology, as you can see. So let me just briefly mention this. So in our problem, we have this SU2, right? We take large K, and the point is that large K, this SU2, WZW model gets geometrized. So its metric is just given by this metric of the 3 sphere, whose radius is K times alpha prime. So at large K, this radius is very large. So now we have a large 3 dimensions just as somehow as our universe. So it has cosmology, and furthermore, we have RD, but we can replace that RD by some time direction. So now we have a time dimension coupled to the 3 large dimensions. So that pretty mimics our universe. And by studying the result in the time dimension solution, we hope that we can have some implications in cosmology. That's another work in progress. So this is the thing I want to share with you today, and thanks for your attention.
So here you want this SU2K to be just the space. You are not studying a non-compact version by hand, say, do an analytic continuation in psi. So that would be another way of having a time dimension, have some SU11.
Right. Yeah. Yeah. We should have some extra time dimension.
Do you have any other questions?